start here. We're talking about killing something.
Yes. What I will be killing is a vortex, and I will try to give you some rough idea what a vortex is. In general, maybe as a disclaimer, there's a lot of violence in this talk, and most of this violence is towards math itself, so I will just make very rough estimates. I try to give you only the ideas because the proofs are kind of technical. So I will try to give you some idea how the proof works, but it will mostly be in pictures, and I spare you all the technical definitions. So if you don't understand something, it might just be because I just glanced over some detail. Please be okay with that. I guess you don't have a choice. So let me start with a motivation, and as lots of us maybe do, is I look at some a more applied field in this sense, in this instance, statistical physics, and they have a problem that stems from looking at crystal lattices, called the dimer problem. So what is a dimer? What's the dimer problem? So the idea is you have some lattice here represented as this big grid, and you want to fill this thing with dimers. Dimers just being like molecular connections between two atoms, if I'm correct. And then you just fill these guys in to the grid, for example, like this. And now what you're interested in, because it's statistical physics, is the total number of different ways to fill your lattice with dimers. So as you can imagine, even from this small example, there's a whole ton of different ways to fill up this thing with dimers. So it's probably not an easy way, there's probably not an easy way to, in general, figure out how many of these structures there are. And that's kind of the first point. One of these is, so if you look closely at my dimer, you can see it's just an edge between two vertices. So if I fill my lattice with dimers, I'm essentially just asking for a perfect matching in my graph. So you could say answering the dimer problem is essentially just counting the perfect matchings in my graph. And that turns out to be essentially the prototypical problem that's hard for counting. So counting perfect matchings is essentially the same thing as computing the permanent of a 0-1 matrix. And that's led to the invention of the class sharp P hard by Weyland in 1979. And that's essentially just the first problem that was proven to be in this class, the dimer problem, or better, the counting of perfect matchings. So the entire talk will kind of look at the counting perfect matchings problem, but mostly do structural graph theory, and at some point come back to this. Not just at some point. I want to start by giving you an overview of what do we know about algorithmic results regarding the dimer problem, or regarding counting perfect matchings. And I think the most classic result in this regard is Castelline's theorem on Caffeine orientations. So Caffeine orientations are just an orientation of some graph in such a way that kind of the orientation itself tells you how to manipulate the adjacency matrix, such that you can just take the adjacency matrix, manipulate a little bit, compute its determinant, and then if you just do some transformation for this determinant, it just gives you the number of perfect matchings. So you can think of this as a way to express the number of perfect matchings as the determinant of some matrix. And what Castelline proved initially was that every planar graph has such an orientation. So for every planar graph, I can make this transformation, and I can find these orientations on planar graphs in polynomial time. Thereby, I'm able to count perfect matchings on planar graphs in polynomial time. In his, this is a couple of papers he published. I think the first is from 61. I just mentioned the 67 here. I think in the first one, he also mentions that this entire approach can be used for graphs on surfaces of larger genus. So it doesn't only work for planar graphs, it also works for graphs of higher genus. He just said it's possible. He didn't give a proof or a construction. The first proof of this was found by Golluccio and Löbel in 89, so quite some time later. And what they do is, instead of using one determinant, they produce a number of orientations, namely 4 to the g many, use all of these determinants and build a linear combination of the determinants to produce the number of perfect matchings. This leads to an Fpt algorithm to count the number of perfect matchings on graphs on bounded genus surfaces, where Fpt generally just means the running time of this algorithm is just some function depending only on g, and then some fixed degree polynomial depending on the size of the graph you put in. Where you can imagine if I need 4 to the g many orientations, that's probably not a good function, but we don't really care. Right? So this is generally, if I say Fpt, I mean a running time somehow like this, where the parameter in this sense, the genus, is kind of decoupled from the degree of the polynomial itself.
So to do this, we only knowing the genuses,
Only knowing the genus.
So we don't need structure of how to do that, right?
Yeah, there's kind of, in this entire thing, you assume that you're given a embedding, but there's also an algorithm that, given a graph of bounded genus, produces an embedding. This you can kind of run, and this works.
So the second result assumes this combination of good orientation is given.
Oh no, they find it. They give a way to find it.
So then how the two contradict with each other? So you said the planar graph,
Yes.
the finding an orientation is cannot be done in polynomial time.
It can.
It can.
It can. For planar graphs, it can. There's like some graphs where we don't know how to find the orientation, but for planar graphs, the proof here actually gives you an algorithm that produces the orientation itself. That kind of works via using ear decompositions of planar graphs. There you have some nice arguments to produce this orientation.
And then the previous slide you showed this grid. It's also planar.
That is a planar graph, yes.
Yes. So then there is a polynomial time algorithm.
For the planar graph, yes.
Okay.
Exactly. That's kind of why. So Castellan himself was not a graph theorist; he's a physicist, and that's kind of the motivation. So he came from the dimer problem. He looked especially at these planar lattices, and then solved it on his planar lattices. I guess it's kind of a kind of useful case in if you look at crystals. Not that I know a lot about crystals, but
when you say linear combination of 4 to the g orientation, do you really mean that permanent is equal to the linear combination of the determinant of?
In some sense, yes, it depends. So for bipartite graphs, the permanent of the bi-adjacency matrix is exactly the number of perfect matchings. While for non-bipartite graphs, you have to make some construction to make there's some more stuff involved, but in the end, it's the same thing. The number of perfect matchings equals this, I think the square root of this linear, or something like this. There might be some factor involved. Yeah. So these orientations you produce here are not Pfaffian, but they kind of behave in the same way. In general, graphs on like the torus itself are already non-Pfaffian. We can kind of extend this idea by saying, let's add some apex vertices to my graph. So an apex vertex is just a vertex that sees a lot. Kind of, you can imagine it is in these pictures, just a small set of vertices that has a large neighborhood kind of distributed inside of my graph. And if I delete this set A, then I get a graph that's planar or has some bounded genus. And what I can do is I can essentially, because the size of A is bounded, what I could do is I could just guess all of the different ways to cover the set A with disjoint edges, then delete the endpoints of all of these edges. What remains is a graph of bounded genus, or a planar graph, and on this graph I can count a number of ways to extend this small matching I guessed to perfect matchings, and thereby produce the total number of perfect matchings in my graph. And this will lead to an XP algorithm. When I say XP, I mean the degree of the polynomial suddenly also depends on some parameter, in this case on the size of A, because I need this size of A to guess all of the different ways to cover my edges in the apex set. And now you could say maybe this is a bad sign, this looks kind of bad. What is A, if A is really big, can we not do better? And it turns out this very easy, like straightforward algorithm that I just described, by just guessing all the ways to cover A, then delete these and count the matchings in the rest, that's the best possible algorithm we can find. So that's done by Caffeine and Chia, and this is already 2015. So you can kind of see that there's several large gaps. 67, first time we find something for planar graphs, then like 30 years later, found a genus, and then even way later, we get apex graphs.
So
yes, can go back.
Maybe you want to say n to the a plus constant?
Yeah, this is O of A. There's some more involved. It's just to give you a rough idea on how the function looks. Okay. So this is what we had like in the more topological sense. Let's go one step further. On what other classes can we compute matchings? So one way to do it could be to use tree decompositions, which is like a very well-used tool in algorithms on structured graph classes. Just to give you an idea what a tree decomposition is, it's just a tuple where t is a tree, beta is just a function that maps to each vertex of the tree a subset of the vertices of your graph G. And then you satisfy essentially two conditions, one of them being that every edge has to be a subset of some bag. And whenever you look at some vertex of G, then the subtree of T induced by all of the vertices whose bags contain V must also be a tree, so it must be connected. Then some sort of consecutivity in the way you decompose. And the width of such a tree decomposition is then just the maximum size of a bag. Tree width is then the minimum width over all tree decompositions. This nice thing allows you to do algorithms. Essentially dynamic programming, right? You just have these small sets, you just guess all the partial solutions in the small sets and then just go from the leaves towards some randomly chosen route in your tree decomposition. And in particular for counting perfect matchings, this again gives us an Fpt algorithm where now the parameter is the tree width of your graph. The nice thing for this is that it's kind of still linked to graph minors in the sense that there's a duality theorem that says a graph has small tree width if and only if it excludes some planar graph as a minor. In particular, if I say some planar graph, I can describe this containment as the existence of a grid minor, grid being this structure here. So I have a universal kind of way to encode what type of obstruction, like what type of graph I want to exclude. In this sense, I have small tree width if and only if I exclude a minor of some grid. And then the size of the grid kind of determines the tree width up to some function. So this is tree width. So we had graphs on surfaces, we have tree decompositions. The last part of what is known is kind of a combination of both of them, which are called the single crossing minor tree graphs. So what we have here is a tree decomposition where some of my bags are of small size, and then there are bags that are very, very big. But if I look at the graph induced by these bags, these graphs are planar. Also, the intersection between the small and the big bags, and also between big bags, are extremely small. These have been characterized as like a part of the graph minor series by Robertson and Seymour to be exactly the graphs that exclude a minor of a graph like this. So we have a grid again as our universal abstraction, but we enhance the grid by a single crossing somewhere in the middle. That's where the name single crossing minor tree comes from, so that's the single crossing. And again, we can use dynamic programming, and now the idea is just to treat to take the method of Pfaffian orientations as a subroutine for all bags that are large. There are some ways to encode the partial solutions from below in some gadgets that you introduce. So again, what you kind of do is you just do your dynamic programming technique, and whenever you encounter a bag that is large, instead of just guessing all solutions, you find a way to encode partial solutions from below onto your planar graph, and then use a Pfaffian orientation type argument to produce the new combined partial solution. So this is again an Fpt algorithm. has been done by two sets of authors, Caffeine and Staub et al. In the same year, actually. I think the later one is the only one that's published. The other one's just an archive paper. They one of the two lost the race, I guess. And that's kind of the extent of what we know on the positive side. The main argument to take away from this is that we don't really rely on decompositions having small width. We still can do something if the unbounded size bags have some additional property. In this setting are planar. Then still there is something we can do. The next question kind of could be that so far we have seen whenever we exclude a certain type of minor, we get a polynomial time algorithm. So the next question could be, is in general excluding a fixed minor, does it always lead to a polynomial time algorithm? And sadly the answer is no. So there is a limit to what we can exclude to produce nice algorithms. And this is a very new idea. This paper is from 2021, I think, the archive version. So what we do is we take a planar graph, like this guy, we fix a face. In my case, I just fixed the outer face of this embedding here. And then we just duplicate all vertices on this fixed face, like this. We make each copy adjacent to the original vertex, and also between two adjacent guys, we introduce all of the connectivities, and all of the connectivities of the original guy are also preserved for the copy. So we call this a ring blow-up of a planar graph. And you can see this quickly becomes non-planar. So there's kind of a way to get from planar graphs to non-planar graphs in a somewhat controlled way. And it turns out, like the published version is from this year actually, that counting perfect matchings on the class of ring blow-up graphs. So ring blow-up graph in general is a subgraph of some ring blow-up of a planar graph. So if I just take all of these, I get the ring blow-up graphs as a whole class. And here counting perfect matchings is sharply hard still. So this is not far away from being planar, but already we can't do anything. And now I said it's about the limit of excluding a minor. If I now look at these very, very sharply, I figure out that these ring blow-up graphs are all minors of so-called Y-grids. That's a class that has been studied like long ago. And these have been proven to be K8 minor free. So this means if I just exclude K8 as a minor, I still contain all ring blow-up graphs. And therefore, on K8 minor free graphs, counting matchings is still hard. So there's like a very strict limit to what I can do. And just as a side remark, these Y grids are minors of a construction like this. So a grid with this jump kind of structure on top. And the reverse is also true. So every such guy is contained in here. So it can kind of go between the two by just sacrificing a little bit in size. And this structure here will become important later on. It's just to say we do have some limit to where tractability lies for the counting matching problem. We have some classes where it works. We do know a class where it doesn't work. And now the challenge, of course, is to fill the gap, to fully describe where does it work, where does it not work. Where does the dichotomy of counting perfect matchings lie? To figure out how this dichotomy, what this dichotomy looks like, it might be a nice idea to just in general consider the existence of these three decompositions with additional structure. And the first thing that comes to mind is like the original structure theorem for H minor Greek graphs by Robertson and Seymour, which gives a structure of graphs that exclude a clique minor. So here I just have a clique and just give you some rough idea what the structure theorem looks like. So Robertson and Seymour proved that if you exclude some fixed clique as a minor, then your graph has a tree decomposition. So here's my tree decomposition, where some of the bags may have small size, and then you have these large bags here. And these large bags have several attributes to them. First attribute being that if they're of unbounded size, they can be of bounded genus with some additional stuff. So the first thing we get is we get to add some handles and some cross caps, in contrast to the structure theorem for single crossing minor free graphs, where we only looked at planar graphs. We also get to add some apex vertices. So we can have some vertices that just hover above our bags and see everything. And finally, and that's kind of the weirdest of the three ingredients, we get so-called vortices. Just a small number of them of bounded depth, whatever this means. I'll get to this later. Just essentially, you can imagine these things as local ring blow-ups, as the thing we have seen before. So locally, we have this embedding of our graph on a surface of bounded genus. After removing some ATCs, then we fix some of the faces of this embedding and perform something like a ring blow-up operation, but only a bounded number of times. And that's the entire structure we have. So if I exclude a click, I get such a decomposition. The problem is, we know that excluding K8 is already not strong enough. So excluding K8 gives us such a structure, but its structure doesn't allow us to count matchings. But still, we might be able to use this as a departure point for our algorithm. But before I go to the algorithm, maybe there's some deeper thing to learn. And by deeper, I mean we might just want to regulate how these three ingredients, vortices, APCs, and bounded genus, appear in our 3D composition. So I define a family of parameters here, which I call tree-width S, where S is a subset of V, G, and A, where V just stands for vortices, G stands for genus, and A stands for apex. And this parameter is the smallest number k, such that my graph G has a 3D composition where for every bag, if the bag is large, then all the parameters that are in S are bounded by k on the torso of B. Torso meaning I just take the bag B, I look at the intersection to all neighboring bags, and I just make the intersections into clicks. So that is what my torso is. I look at this specific graph. In this graph, I want all the parameters that are in S to be bounded by k, and all parameters among V, G, and A that are not in S should be trivial. So as an example, if A is not in S, then I should have bounded V and bounded G without deleting a single apex.
Do you want S to be a subset of VGA or?
Ah, yes, sorry, it should be a subset. Yeah, not an element.
Okay.
Yes, so I'm allowed to take several of them, of course. We have some examples of this parameter. For example, if I take V, G, and A, so S is the full set, then I just get the class of all graphs, like all minor free graphs. And this parameter I generate, so tree-width VGA, is parametrically equivalent to just the exclusion of some click minor. Similarly, as we have seen, if I just take the grid with a single crossing in the middle, I get a parametric obstruction, so these two things are again somehow the same. There, my S is completely empty, so all of three parameters should be 0, meaning no vortex, no apex, and genus should be 0, meaning I'm planar. So that's the single crossing minor free case. And then, of course, I kind of get the entire hierarchy of these parameters in between. So there's one famous parameter I kind of left out, which is tree-width. Tree-width is kind of a hack that we apply. So the definition here says for every bag, if the bag is large, then it has to satisfy a property. I could also just say I replace this property by a false statement, thereby forcing all bags to be small, and that's exactly tree-width. So if I just write false instead of anything here, I get a parametric equivalence to excluding a large grid, kind of completing this picture of VGA hierarchy. And this is, I think, the more abstract contribution of our work. What we will be focusing on is this part. As we've seen before, genus is kind of fine, APCs are kind of fine, just these ring blowups are bad. So maybe if we get rid of the vortices, we can get something. So that's what we want to do. That said, maybe we should first verify that getting rid of vortices allows us to count perfect matchings in the first place. Yes, I was a bit too fast. Just as a statement, so I want to introduce to you what are we proving actually. So here's this guy again that we had before, like just a big grid with these small jumps on the top. I call this a shallow vortex grid. And the size of the grid is just the row, or like this is square grid, like this is k by k with these guys on top. And I can define a parameter for graphs. I can say Vm of G is just the largest number k, such that G has a shallow vortex grid minor of order k, which it should say there, it does not. Order k meaning it's like the k by k grid completed with these jumps on top. And then what we prove is a structural theorem first, that says this parameter Vm is actually equivalent to the parameter here, where we forbid the word vortices and just allow genus and APCs. So that is the universal abstraction for this specific point in the hierarchy. So kind of you can see a trend, right? In all of these pockets we get a universal abstraction, usually a very simple one that kind of mirrors the grid theorem that was proven for trees in the first place. Just a more slightly general version of it. And then we of course apply this structural theorem to prove two things. The first one being, if I have a minor closed class C that excludes some shallow vortex grid, then for this class there exists a polynomial time algorithm that computes the number of perfect matchings. So whenever I exclude such a guy, I get a class where I can count matchings. And the opposite kind of also holds. If I have a minor closed class that contains all of these grids, then counting matchings is hard. So these guys are indeed exactly the things that make the dichotomy for counting matchings happen. Which is a very nice thing, because this now kind of puts an end to this entire journey of counting matchings in minor free graphs. So now I promised maybe we should first verify that having a vortex-free decomposition allows us to count matchings. So here again is a big tree decomposition with some bags of bounded size. And then I look at the torso of a large bag. If this has bounded genus after deleting a small apex set, then like just on this torso I am actually able to use the strategy of Gallucci and Löbel to produce the number of perfect matchings. And now I just need to use the dynamic programming strategy that was used for tree width and then later for single crossing minor free graphs to combine the two. There are some technical details here, because still I need to find a way to encode like partial solutions, say from this subtree, on the torso of this graph to be able to use the orientation method to produce my number of perfect matchings. We do this by essentially not just computing the number of perfect matchings, but what we do is we produce the entire generating function of weighted perfect matchings in the graph. And then if the weight is just all ones, the generating function gives us the number of perfect matchings. But doing this more general thing allows us to resolve some other computational problems and kind of helps with this technicality here. And this, in the end, will give us an XP algorithm for graphs where the GA tree width is bounded, where the parameter for this algorithm is just this GA tree width itself. Again, you might ask, maybe this XP can be made into FPT, but we contain all apex graphs as a special case, so that's the best you can get.
Sorry, what XP means? It's an exponential with respect to size of apex.
It means that the running time of the algorithm is of this type, size of the vertex set to the power of O, and then here is tree width, GA. Some function of it, actually. So this is the running time. So once you fix this, this becomes a polynomial, of course.
Are you going to explain what vortex is?
Yes. Yes. Actually, now.
Yeah.
Of course, like so far I've kind of abstractly told you if I don't have a vortex I can do things. So maybe now it's time to figure out what a vortex actually is. Just some warning. This slide essentially contains the proof of the graph minor structure theorem, just very roughly. I will try to make it work, bear with me. Just the general gist is this entire structure theorem is proven by induction. And the induction kind of works by iteratively finding large sets of disjoint paths between vertices. And eventually I will run out of these paths because my graph is finite. And the vortices, very, very much brought down to earth, are just the areas where I don't find enough paths. So I can't continue my proof. That's what a vortex is, essentially. So this is why I say it's kind of a byproduct of the inductive proof strategy for GMST. It's also something we can't avoid. The original definition of vortices, before I go on into the slide, is slightly different. So the original definition was you get some phase on your surface, and in this phase there's a path decomposition, kind of curled up like a ring, where all of these sets are small. That's the original definition of a vortex. The one I'm giving you is slightly different, and it originates from a new proof of the graph minor structure theorem by Kenichi Kawarabayashi, Paul Wallen, and Robin Thomas. I think the archive version is from 2017, and I'm not sure if it's published yet. But that's like a groundbreaking work. They kind of are able to condense most of the graph minor series into a single paper. So if you want to learn something, I really recommend reading this, called Quickly Excluding a Non-Planar Graph.
It's not published yet, by the way. I mean, at least it wasn't when Paul talked about it 2 weeks ago.
Oh. Yes.
Months ago?
Big fan of this paper. Okay, let's try to summarize what they did in 100 pages on one slide. So the main idea here is the so-called two-path theory. So given some set of vertices, imagine you want to draw your graph such that these set of vertices lie on a cycle given a fixed order of the vertices. And now you ask the question, under which circumstances can I do this such that the graph is more or less planar and these kind of sit on one face? And turns out there is a very nice structural characterization of this, meaning this kind of substructure, so these two disjoint paths crossing each other with respect to the ordering of my vertices, does not exist if and only if I can kind of take whatever is inside here, press down on it, and make this into a planar embedding, modulo kind of cutting out things that attach to a small set of vertices. So in a three-dimensional point of view, you could imagine this as you have some disk, you have a fixed set of vertices that sits in a fixed order on the boundary of the disk, and the entire rest of the graph is either drawn in a planar way onto the disk or connects through a separator of order at most 3 to something that kind of hovers above. The separator of order at most 3 kind of allows you to just delete everything here and make what is left into a triangle bounding a face here. So this is kind of what the flat is. So it's kind of close to the idea of planarity, modulo things that attach to small sets of vertices. This roughly explains the structure theorem for single crossing minor free graphs. That's exactly what happens if you exclude a single cross. You get something that's planar plus things that attach to it in a tree-like fashion. Okay, so this is what flatness means. That's also known as the two-path theorem. And that's the main argument we're going to use. So the first observation is, given some big grid where we have a lot of like local crosses somewhere spread out, then we can use the big infrastructure of our grid to use all of these crosses to build a click miner. I'm not going to give you a way to do this. It's just possible, let's say. And this kind of transpires. So many spread out crosses allow me to build a click miner. Similarly, kind of not on the slide, but I can do it here. If I have a grid where I have many disjoint paths that kind of jump far in my grid, then I can also build a click miner. So these two situations cannot happen if I exclude a click. Also, suppose I'm already given some part of my graph here, many disjoint cycles that kind of sit nicely arranged, and I attach a new part, like these parts here, to the thing, then what I get here in the two intersection points are again very large grids. And I can use this observation I made here to essentially just make counting arguments and say, if in here I find many crossings, I can build a click miner. So I will not be able to find many crossings in here, meaning just by the large size of it, I find a strip that's again free of all crossings. So I can use the two-path theorem to press down on it and kind of fix it to a surface. That's what I mainly what I mean when I say flat. Essentially, I just find large substructures on which I can press down, and then it's roughly embedded in the surface after possibly deleting some apex vertices. And roughly embedded just means I have these weird attachments to small separators. Okay, so this happens. So whenever I attach something like this, whenever I find a large linkage that kind of crosses through a non-embedded part, I can make my counting argument and I find a flat thing. So one of the outcomes is I could just find a click miner if I find a large linkage like this. What could also happen is that I find two linkages that kind of cross over like this. So I find two linkages that kind of together they build something that's not planar. I cannot draw both of them at the same time. And I will call this just a handle. Similarly, what could happen is that it has found a lot of paths that are pairwise crossing. Similarly, I can just take the part where they're pairwise crossing, I can kind of untangle it, like just cutting through a Möbius strip and making it into a normal strip. This I can press and then I twist it again and glue it back in. This will give me a cross cap. And again, kind of the observation is if I just have enough of these handles and cross caps, what I will get is again a click miner. To get an understanding of this is just look at this picture. This picture essentially just says is if I find many crosses that are far apart, I can build whatever I want. So and all of these things just contain a single cross each. Like they actually contain many crosses, but I can never find two disjoint ones that are next to each other. All of them are kind of interwoven. But if I just find enough of them, then I get enough instances where they're far apart, and then I can again build my large miner. That's kind of the main idea. And the last idea is maybe what happens is I just find the thing I can press down upon, so this is flat, and then it kind of splits the non-embedded area into two, each of them containing a cross. But there's nothing that communicates between this side and this side. That's like the last outcome that might happen. And if I split my non-planar area many times, then I kind of reach the case where I have many spread out crosses again. So I again can build a KT miner. So even this splitting cannot happen a lot. So what I do is I iteratively just add more and more linkages to my graph, thereby kind of extending the almost embedding I have, until at some point in each of these split areas, I just don't find a linkage anymore that's large enough. And that kind of forces me to stop. So inside of this area, here's an example of this. I could still find lots of disjoint paths and I just do some chaotic thing, but I cannot find this structure here that's kind of nicely arranged. That stops me. And that's what I will call a vortex. So this thing here is a vortex. The depth of this vortex is just the order of a largest linkage that I can find in here. So the depth of this vortex would probably be, I think it's 5 or 6. Yes, 6. I could take these plus the pink one like this plus this one. So the main idea is the linkages I need to extend are, if you look at the boundary of my disk, I want to have 2 consecutive segments of my disk that are linked by paths. So this type of linkage is the one I use. and if I don't find it anymore, my depth is bounded. If the depth is bounded in this way, then I can build the original definition. So there is a way to reconstruct this weird path-like decomposition because I find small separators. But that's roughly the idea. So this is where my vortex comes from. Looking at the time, I probably don't have a lot of time to go into the proof. So just give you some very, very rough idea. But maybe you have questions at this point, because I think this is a slide that raises questions. If not, I continue. Okay, so we now know what is a vortex. We know we can kind of start with the assumption that they exclude a large clique, because if we have all cliques, then we contain everything. Thereby, we can kind of assume we already are given the structure theorem of Robertson and Seymour. And what we want to do is we want to refine it by removing or killing the vortices that appear. That's where the title comes from. We don't build it from the ground up. We kind of go to the top level and then go down. What the proof does is it kind of gives us for each vortex. So imagine the red thing here as the boundary of a disk, and inside of the disk is my vortex. And each of these vortex disks is surrounded by a nicely embedded family of cycles like this, called a nest. And I want to make this nest tight, in the sense that I cannot push it closer to my vortex. So what I do is I find a large linkage from the outer disk to this vortex, and I find a minimum separator, cutting the outer vortex and the outer cycle and the vortex apart. Since this part of my graph is essentially embedded on a disk, it gives me a closed curve, so you can imagine it as this pink line. And by Menger's theorem, the size of the orange linkage and the size of x are the same. And I can just say if x is small, then I can just throw away whatever is inside and push it deeper down into my 3D composition. So I can assume x is very large. And now what I want to have is that this pink area here still defines me an area where the depth is bounded. So I know the red part has bounded depth, but I want the pink part to have bounded depth. I want this part to exclude large linkages. So what I do is I just assume there is a large linkage. I do know, because the red part has small depth, that most of this large linkage cannot go through it, because otherwise I would have found a large linkage on the red thing, which is forbidden. So most of it kind of must avoid it, go left and right. And then what I just do is I use this thing that kind of surrounds my vortex to push the nest structure, like the entire family of cycles, kind of closer to this disk, to create a extremal situation. Because my graph is finite, this procedure must stop at some point. So at some point, whenever I cannot find a large linkage anymore, because each large linkage will allow me to make the nest tighter, thereby slowly removing vertices from the inside. I stop at some point, and then I know the pink curve has bounded depth. Yes. So how do I use the bounded depth? How do I actually construct my forbidden minor? Because this is kind of the key of my strategy. What I want to say is, if I have a vortex, then either I can remove the vortex with a small number of vertices, or I find the forbidden minor. So I find this big grid with the many jumps on top. And for this, I just use a counting argument, essentially. So I know that because of the bounded depth of my closed pink curve, whenever I fix some segment here, I cannot have many paths that go from here to the complement. So I can kill all paths that go from y to z with a small set S, and thereby kind of isolate this area. Because of this observation, I can just choose my first segment here, y1, to be minimal with the property that after I delete the separator S1, whatever is inside here still has a cross on the pink curve. If I don't find such a cross, if such a segment does not exist at all, then I can just delete a small set of vertices, get rid of all the crosses, and then I'm fine again, because then the vortex is done. Also, because of the minimality of y1, if I just go one step in and also take r1, which is this part, I remove all the crosses that interact with this part of my graph. So at the same time, I can force the existence of a cross, and I know that there's a small set of vertices that removes all crosses that are inside of this area. And then just continue. So once I've selected this set, like this segment, I just build the next segment here with the same property. So this should be the smallest one, such that after deleting this in the graph where this is already deleted, here is a cross. And I continue doing this. And just get a large collection of these guys. So each area will have a cross, a small hitting set for all crosses that are inside, and these areas by construction are pairwise disjoint. And this finally leads me to the nice dichotomy type thing where I either find just a small number of them, eventually I just run around my circle and meet myself again. If I find just a small number, I can delete all of the sets I've collected to remove all crossings that occur in my vortex altogether. Or I find many of them, and this means I find many disjoint crosses that are kind of serial on my curve. So going back to my construction from before, I use this procedure on the pink curve and thereby find these nice separating areas. Here will be my my crosses, and there's the stuff inside. So what could happen is that I only have like few crossings. If I only have few crossings, then I kill the vortex. I just delete all of these separating sets, and whatever sits here and whatever sits inside here is just sent deeper down into my 3D composition. And all of these parts, because I've deleted all crossings that occur, have a planar embedding anyway, so I can just make it part of my nice embedding in the first place. So few crossings allow me to kill my vortex. If on the other hand I find many crossings, many here being the same number as few, I do know, because this part here is nicely embedded, that the actual crossings only occur inside of my vortex. That's important, right? Because I need to use this entire grid structure here to build my abstraction. I need some grid in my abstraction, if you remember what it looked like. It was kind of this situation here where you had a large grid, and then you have this type of thing on top. The crosses will ultimately become this, but the grid structure also needs to come from somewhere. And that's kind of the reason why we chose this curve to sit on these orange paths. This gives us the right to say, okay, all of these crosses sit on the pink curve, meaning we can always extend the ends of these crosses down to the outermost cycle of our grid. This spares us a lot of arguments later on, because then we just take the crosses, extend them, and get a structure like this. And now if you stare at this long enough, you will find this guy inside. So this gives us our shallow vortex grid. And that means this is a forbidden outcome, right? If we say we forbid this guy in the first place, this path here can never happen. So for each vortex, this path will occur. And because we only have a bounded number of vortices, we can kill all of them with a small set. Yes. I said that the parameter 3 with genus apex is equivalent to forbidding a shallow vortex minor, so I also have to give you a proof that if I have a shallow vortex grid as a minor, my parameter is large. That's the sufficiency part. So by now we know no shallow vortex grid means small cleavage GA. I just use this guy again, but you can construct this guy from this as well by just sacrificing some numbers. This guy does have a very large grid, and intuitively this means I cannot make a 3D composition of small width that decomposes this entire graph into many different bags. So most of this graph must sit in one bag, or at least close to this, then everything must be close together. And here I give a construction that says, take the green part, contract it into a vertex. Take the orange part, also contract it into a vertex. And take the pink part, also contract it into a vertex. So you get 3 vertices, the green one, the orange one, and the pink one. And now take all of these blue guys, also contract them into single vertices. Well, the resulting graph is a K3R, where the one side, the three vertices, are the green, the orange, and the pink one, and the other side of size R are all of the blue ones. So even if I delete some vertices from this graph, because the number of these crossings above is large and the grid structure is extremely large, I cannot remove this substructure completely. And thereby, even by deleting a small number of vertices, I always end up with a K3R minor. This kind of brings up the genus of my graph. So neither can I have like a nice tree decomposition, nor can I just, after removing a small number of vertices, produce something that's of bounded genus. So no matter what happens, yes, that's what I just said. No matter what happens, the parameter tree width genus apex will be large. So that's my sufficiency, and I think also my time is almost up. So just finish with kind of an overview what we have done and what could happen next. So here again is the VGA hierarchy, now with the new member of our abstraction set, the shallow vortex grid, as kind of the new grid-like structure. And what we did was we proved this line of separation. Any graph that you look at has one of these parameters bounded, or any class and any proper minor-free class. If you are below this line, then you know that there's a polynomial time algorithm to count perfect matchings. And if you're above this line, you know counting matchings is hard. So this indeed is a dichotomy result for counting perfect matchings. So a natural question would be, is there anything else we can do? Maybe this structural theorem here allows us to produce algorithms for other problems. Just to give you a hint at this, for tree width we have, for example, Cosell's theorem, so we can solve a lot of problems in Fpt time actually. For single crossing minor free graphs, there's no meta theorem yet, but there's a lot of different problems we can solve in polynomial time if we exclude such a grid. For the shallow vortex grid, so far the only one we know is counting matchings, but there's no reason not to believe that there might be something else. And then the second relatively obvious question is, there's of course 5 more guys left. What can we do with these? What are the abstractions? What type of problems can we expect to solve in polynomial time if one of the other 5 parameters is bounded? So what is the complete picture of this hierarchy? And that's it. Thank you.
Thank you. Any questions?
Which problem can be solved easily for the single crossing case?
I think for me the most interesting one would be max cut. So far for max cut, this is kind of, so everything below is kind of the most extent where we know we can solve it, except for like special cases. The current conjecture is that max cut can be solved in this ideal here, like in this set. So people believe the only thing that obstructs max cut from being solvable is the apex vertices. But so far, that's what we know.
Do you also have any rough idea for the obstructions in other cases?
We think we know all of them. We are lacking the proofs.
Do you want to be off the record or not? No. Okay, go ahead.
We're lacking the proofs of these 3. So these 3 you can prove. We think there might still be a problem.
I see.
But so far we are pretty confident in these 3, and the other 2 are a bit more complicated, especially this one. For this guy here in particular, maybe this is interesting. There is a structure theorem out there that says if you take a grid and you exclude the grid with a vertex that sees the entire grid, this is kind of seen as the prototypical apex graph. If you exclude this, the structure theorem says you're not quite here. So you might still have APCs, but all APCs you have only have neighbors inside of your vortices. So what could happen is that you get a bag that's embeddable on a torus with, let's say, 2 vortices, and your apex has neighbors in both of them. So if you could reduce either the number of vortices or the neighborhoods of the apices to just one vortex, then you would reach this point. So far, there is no proof of this.
So can your research generalize to some other kind of counting problems over graphs?
I do know that there is a group currently working on this. I don't really know. I'm more on the structure side. It's like the first time I actually went into doing something with counting problems. It might be true. There are some reasons to believe that this should generalize, because for many problems somehow things become difficult once you encounter vortices, because these are kind of chaotic structures, and it seems to be the case that in general counting problems are kind of find the limit there.
Let me just make sure I understood correctly. So
Yes.
when you forbid that this shallow, what is it? Shallow
Running time, and it either finds a clique minor of size t or produces the big decomposition that has the vortices.
Yeah.
And our approach to kill the vortices is constructive. So this gives a polynomial time algorithm to take this decomposition and get rid of the vortices.
Still running? Is this still Fpt?
I think so, yes.
Uh-huh.
Yeah. So just to get the decomposition, I think we can do it in Fpt time, yes. Because if I just go back a little bit, essentially what you need to do is you need to
Menger many times.
yes, it's just Menger. So you need to find this, which is just reapplying Menger, and then you go into this setting, and this is just Menger and 2 path. So I think this should still be even in cubic time.
And you have to do this for every vortex, but no more vortices is still bounded.
It's a constant, yes.
I see.
Yes.
So for this XP algorithm, roughly what's the dependence on the, do you have like an explicit anything, or is it very...
We do have explicit numbers. So there are some papers that kind of make a trade-off between depth of vortices and genus to number of apices you have to delete. So you can kind of switch the numbers around. This proof was the first one that gave concrete bounds for all 3 parameters. And this was a tremendous effort.
Yeah.
I think there is still a lot of room for optimization. The question is whether you want to do it.
Like, did you think about like possibility of proving this without using that paper?
We shortly thought about it. You need to get to the point where you get the bounded genus decomposition with a small apex set. You need an engine that finds you these decompositions, kind of rooted at a big wall that you find. The only other method to get these kinds of decomposition that's known so far is the original graph minus proof. That is even more complicated than this one. I think if you find a version that does not rely on this, then you would also find an easier proof for graph minus. We just looked at this, we concluded this, and then just went with what was there.
Any other questions? If not, let's conclude the speaker.